The type of force. But how do we find the type of force? How did we identify our type of force? This was what we spent a large portion of yesterday doing. We had to come up, fair enough, what we talked about on Tuesday. We looked at the type of bond. So what we have to do is look at our compounds and identify the types of bonds present. What are the types of bonds present in the first molecule, 2A? Careful, types of bonds first. We have carbon to carbon, we have carbon to hydrogen, both of which are nonpolar covalent. Now that we've established the type of bond, we can jump to the next part, which you're already skipping that first step, Emily, which is good. Okay. That would then get us to London dispersion as our strongest force. We then do the same analysis with the second compound. We still have carbon to carbon and carbon to hydrogen, both of which are nonpolar covalent bonds, which then take us down to London dispersion forces. Have we addressed all of the bonds in 2B? What bond are we missing? In 2B, where's the OH? So I assume what you're referencing is the O being next to the carbon. Okay, this is where knowing our Lewis structures comes into play. Those hydrogens are all bound to the carbon in front of it. The carbon is then bound to the oxygen, which is then bound to the next carbon. Okay. Yes, that is trickier, but that's sort of technically one of the things that we're assuming you picked up when we talked about Lewis structure. Okay. So that means the last bond that we need to include would be our CO bond. What type of bond is that? Psych is a good response on that. Dipole is a force, not a bond. What's our bond? It is covalent. Is it polar or nonpolar? It's polar covalent, because our nonpolar would be same to same. Carbon and oxygen are not the same element. Okay? Or carbon to hydrogen. Oxygen is not hydrogen, which then makes the carbon to oxygen bond polar covalent. If it is a polar covalent bond, that leads us to the dipole-dipole force. Okay. Something to consider, if we find a dipole-dipole force, we should further evaluate and say, do we have hydrogen bonding? Okay. To have hydrogen bonding, what else do I need to have on top of the dipole-dipole force? A hydrogen bound to fluorine, oxygen, or nitrogen. Do we have that?
No.
No. So we don't have hydrogen bonding in that compound. The strongest of those two forces, London dispersion or dipole-dipole?
Dipole-dipole.
Dipole-dipole. I can now kind of ignore that. That was probably a wrong thing to do, to just erase it. But we can ignore that one. We're looking at dipole-dipole for 2B. For 2A, what was our strongest force? London dispersion. Which of those two forces is stronger? Dipole-dipole, which suggests 2B has a higher melting point and boiling point than 2A. Okay. You can almost look at it as sentence level structure analysis that then you scale up to getting to the conceptual understanding. Okay. We look at each of the individual connections of the letters to get us the types of bonds. We can then expand that out to our types of forces and then interpret the forces across. Okay. So spend 2 minutes, figure out 3. So let's walk through the analysis of 3B. We would start with our carbon on the far left. What is connected to that carbon? Okay, which hydrogens? The first 3. Those hydrogens and those, or that hydrogen and the 3 repetition should all be bound to the carbon. If we look at the formula, what is that hydrogen then next to?
Carbon.
Another carbon. Okay. And I'm getting a lot of students will then saying, well, then that hydrogen must be bound to a carbon. Okay. Well, can hydrogen have more than one bond?
No.
No. Okay? So by showing that in our formula, what are we trying to say?
Carbon is bound to carbon.
The carbon is bound to the carbon. The only place where there's an empty slot to draw that next carbon. What is bonded to that carbon?
Two hydrogens.
2 hydrogens. Okay, but carbon's supposed to have how many electrons around it?
4.
8, octet rule. Right now it only has 6. So we're missing something. What else was connected to it? And this is where you jumped in, Chandler. We have the oxygen. So we could then show the oxygen being connected to the carbon. What's connected to the oxygen? That last hydrogen. And we'd have our structure. Okay? It is a bit of a leap going from the formula to the structure, but again, that is what you're expected to do. Are there questions on going formula to structure? Say that again. So when we build our formula or our structure, that's a good point. We start with the leftmost atom of our formula as our center atom, and we scatter the next things around it until we've achieved its octet. And then we move to the next atom. This should have an octet, to the next atom, to the next atom. So we move through the formula left to right in a linear fashion. Yes? Interesting point. The oxygen does not appear to have its octet satisfied. What else do we know about oxygen?
It has 6 currently in its valence.
Oxygen comes in with 6 valence electrons. If we went through and processed and counted out all of the valence electrons that needed to go into this, we'd notice that this bonding structure is coming up with 4 electrons short. Those 4 electrons are 2 lone pairs on the oxygen. That's where it gets its octet. Okay. Questions?
I know this probably isn't until later, but if there are 2 bonds, I guess you could say hydrogen bonds, that like, and you're trying to determine which one is stronger, how would you go about that? Or is that something different?
So that's an interesting concept. I will redress that in just a second. Let's finish out this one. Okay. Now that we have our structure, we should be able to interpret the types of bonds present. The bonds between hydrogen and carbon are nonpolar covalent. The bonds between carbon and carbon are nonpolar covalent. So we could go through and write NPs on every single one of those. Since I already started it, I'm going to. Okay, for nonpolar. All of the nonpolar covalent bonds will generate what force? London dispersion forces. Okay. We also have a carbon-oxygen bond. The carbon-oxygen bond is polar covalent. We're going to write that as just P. If it's a polar covalent bond, what type of force do we get? Dipole-dipole. Just going to bring in the next kind of issue. Our hydrogen, what color can I use? Let's do black. Our hydrogen to oxygen bond is what? It is polar covalent. For it to be nonpolar, it must be carbon bound to the hydrogen. So it is also a polar covalent bond. So we have a second P. If we have a polar covalent bond, what type of force is that? Dipole-dipole. Once we've established we have a dipole-dipole force, then what can we do? See if we have hydrogen bound to oxygen, nitrogen, or fluorine. If that is indeed true, then I have hydrogen bonding. So in the case of the oxygen bound to the hydrogen, do I have hydrogen bound to fluorine, oxygen, or nitrogen?
Yes.
Yes, which means that dipole-dipole force becomes a little bit stronger, and it becomes hydrogen bonding. So for 3B, my strongest force is hydrogen bonding. For 3A, my strongest force was dipole-dipole. I'll leave it to you to break that one down to get that. Which is the stronger force, dipole-dipole or hydrogen bonding? Hydrogen bonding, which then means 3B has the higher melting point and or boiling point. Okay? Kind of makes sense? Okay. To Chandler's argument, Which of these might we predict to have the higher melting point? HF or HCl? Why HF? Oh, actually, sorry, I don't want HF or HCl. I want, whoops, I want HO. Why are you still saying HF? Both of those bond structures are polar covalent. Both of them generate dipole-dipole forces. Both of them satisfy the hydrogen bonding rule. So they both have hydrogen bonding as a force. But our hydrogen bonding force is dependent on the difference in electronegativity between our atoms. Fluorine, being the most electronegative, has a partial positive charge, or sorry, partial negative charge, just like the oxygen having a partial negative charge. So if I drew out the partial negative charge on the oxygen, I generate a pretty big partial negative charge. But if I go through and a partial positive charge on the hydrogen, what would I look at for the fluorine? Well, fluorine's more electronegative. What is it doing to the one electron that hydrogen's contributing? It's taking it. It's taking it even more than the oxygen did, which means what happens to the partial negative charge on the fluorine? It increases. What happens if I have larger charges? It's harder to separate them when we look at the intermolecular forces, because we're getting a stronger neutralization force by bringing them together. Okay? And we'd run into the same kind of concept, though potentially a little bit more difficult to see if we looked at the dipole-dipole forces.
And same thing with ionic.
And the same thing with ionic. Yep. Okay? So, we looked at our heat versus temperature. We could also bring this into vapor pressure. Okay? Anybody looked at the practice exam yet? Oh, the practice exam is in less than 2 weeks.
You mean the real exam?
Fair enough. The real exam is in less than 2 weeks. It is probably a good idea to have the practice exam completed by tomorrow. Tomorrow would be a really good day to have the practice exam completed, because then what can you do over this weekend?
Study.
You could check your answers. You could make sure that the answers that you've selected are correct, either by confirming with the tutor at the tutoring center, confirming with me, which is a good point. I'll talk about that in just a second. Personally, which we'll talk about, or you can confirm with me via email. You can send me a list of all your answers, and I can spit back responses saying, wrong, I don't think you looked at this. Wrong, I don't think you looked at this. Or you get absolutely no response, which usually means
You missed it.
Try again.
you're right.
Oh.
Okay? Because remember, I won't comment that you are correct. I will only comment when you are wrong. Okay? Personally finding me. When can you personally find me? Office hours. When are my office hours? Everybody, I have no idea. It's online. Okay? That's one option. We could look at the syllabus, and you would find office hours for Monday, Tuesday, Wednesday, and Thursday. Do I have any office hours tomorrow?
No.
I do, actually, because I forgot to announce them. I'm going to have really long office hours tomorrow. I will be available from 9 o'clock in the morning till 2 o'clock in the afternoon in the library. Okay, right across the hall from the Science Tutoring Center. I'll be holding extended office hours in there. I would hold them all the way to 5 o'clock in that room, but the library closes. So instead of holding them from 5 o'clock all the way in that room from 2 on, what will happen is that from 2 to 5, I will then go to my office in Agave. Okay? And you can still answer questions. So I am holding office hours from 9 in the morning till 5 o'clock in the evening tomorrow. Okay? Maybe that notice is a little bit too short of a turnaround, so maybe I should do that again.
So you are.
So I am.
What's that?
I can't pull that one. Next Friday, I'll be doing the same thing. 9 to 5. The library is actually open 9 to 5 next Friday. I'll do the same thing, same room. I'll hang out the whole time. If you have questions through the weekend, sorry, I'm not going to show up to campus for office hours, but you can still email me. Okay? I will be posting an announcement about that, hopefully, at some point today so that you can at least reference that and find that help. Okay. Once you've completed the exam, then what can you do? What's that? You could do it again. Okay. The fun thing about doing an exam again is you already know all the answers. So what should happen to your score? It should go up. Okay. Why is it going up?
Practice.
Because you know the answers. That's why it's going up. When you take the actual final, are you going to know the answers? No. So what you should do, instead of taking the exam a second time, okay, which can have some benefit if you haven't memorized the answers already, is look at each question and say, okay, why was it not answer A? What is wrong with answer A that would make me say that is the wrong answer? So instead of going through and finding the right answers, go through and define why the wrong answers are wrong. Why'd you not do that the first time? It takes a stupidly long amount of time to go through and process that. Okay? But answering the questions or finding out why answers are wrong can be more beneficial for a test that doesn't give you the exact same questions. Okay? The next thing you could do, take the question that's asked, change the question so that it's still on the same concept, but it makes one of the wrong answers now right. Okay? Which is exceptionally challenging, but we can do that. And we'll take a look at that process for the question that's up here. Because only a couple people have looked at the practice exam, this question probably won't look familiar. But guess where it's found? On the practice exam. Okay? So we can look at vapor pressure and apply that back to our forces. Okay? What was vapor pressure? Yeah, split it out.
The pressure built up by the vapor coming off from your liquid when it heats up and like the gases come out.
Is the pressure of our gas above a liquid? Okay. What does it mean if I have a high vapor pressure?
Wait, can't that mean multiple things?
It can be a lot of things, yes. So let's figure them out. How could I have a high vapor pressure? And why would I even ask that question? Why am I asking how do I have a high vapor pressure? What's the question ask? Which has the highest vapor pressure? So what we're trying to do is drill down into that question and determine what's happening. Vapor pressure is our first definition that we need to identify. We then want to identify high vapor pressure. So what are the conditions that are going to cause a liquid or a system to have a higher vapor pressure than another?
So, lower boiling point, like needs less energy for boils.
Okay. What does it mean if I have a lower boiling point? A smaller force is required to do what? To boil. So if I have a lower boiling point, what does that mean? If I compare a low boiling point species to a high boiling point species in terms of vapor pressure,
The high boiling point's gonna have less.
the high boiling point should have less pressure. Why would it have less pressure? If it's at a high boiling point, there's no gas. If I'm at room temperature and I have a high boiling point species, there's very little gas because, well, I'm not at the boiling point. Okay? So in referencing this, we're trying to identify the pressure of the gas. If I have a high vapor pressure, what does that mean? What does that mean about my boiling point? Sorry, that's too big of a leap. High vapor pressure means what? Do I have more gas or less gas? More gas. When do I have more gas? I could reference the boiling point. More gas means low boiling point. I could also mean really high temperatures. Can I change the temperatures according to the question? No. Temperatures are relevant to the question, so changing the temperature is a bad thing to focus on. What we'll need to focus on is our boiling point. So I'm looking for a species with a very low boiling point. Well, what dictates my boiling points. Don't quite accept that. Bonds is an important thing, but that's not the next step in this question. Our boiling points and our melting points were based off of our forces. To have a low boiling point, what does that say about the force? Is it a weak force or a strong force? How do I get a weak force? London dispersion is my weakest force, so I look at those and I say, oh, there's the force. What do those structures actually show? Now William and Obed can jump in with your answer. The bonds. To get a weak force, what kind of bond do I want? I want a strong bond, which is the nonpolar covalent force. Because the stronger the bond, the weaker the force that comes out of it. Because we've already neutralized those charges, there's no reason for it to interact with a secondary molecule. So why is this question interesting? We started at vapor pressure with a definition. We then said that vapor pressure definition was a little bit too vague, so we said it means more gas. Well, I get more gas because I have a low boiling point. I have a low boiling point because I have weak forces. I have weak forces because I have a nonpolar covalent bond. And after all of that, now I can answer the question. The answers given only show me information about what? The bonds. So what I want to go through and do is the exact same thing we just did for our melting point and boiling point and apply that out to these to determine the bonds. Because I just said the best answer is nonpolar covalent, I want to go through and look at those and hope and pray that I have a simple answer, that I only have nonpolar covalent bonds in one of those answers, and that all of the other answers have some other type of bond. Because some other type of bond is going to result in what? Some other type of force, and all of those forces are stronger. I want the weakest force possible. Kind of make sense? Okay, so let's take a look at the first one. What bonds do you see in the first one? Simon, you're already shaking your head. Why'd you shake your head so quickly? You see oxygen. As soon as you have oxygen, you're immediately in a polar covalent type of situation, which immediately puts you in a dipole-dipole force. So by seeing oxygen, you can immediately jump and say, that's got to be wrong. What else could you have jumped on there? How about the OH? OH is hydrogen bonding. That's already going to drop me into a stronger force. So A is going to get me a pretty strong force. What do I see in C? I see an oxygen in C, which is going to get me a stronger force. What do I see in D? Chlorine. What can you tell me about chlorine? What's that? Chlorine is one of our higher electronegativity elements. Okay. You may not know that off the bat. Okay. So what else could we do? What is that chlorine connected to? The carbon. Okay. If I have a carbon bound to a chlorine, what type of bond is that? That is polar covalent. Why is it not ionic? They're both nonmetals. Okay. Why is it not nonpolar covalent? Carbon to hydrogen or same to same. Chlorine and carbon, neither of those are hydrogen, okay, and neither of them are the exact same. That means it's not ionic, it's not nonpolar covalent. We must be polar covalent. That's going to generate a stronger dipole-dipole force. The last one you see S. Anybody know the electronegativity of sulfur? It's actually not that much. I honestly don't know it off the top of my head. but we don't need to know it. And this was one of the reasons why we went through and identified those rule of thumb bond definitions on Tuesday. What type of bond am I going to get between sulfur and carbon? A polar covalent bond, which then is going to generate a strong force. Well, this kind of sucks. 4 of my answers are all saying a strong force. What does B have? Carbon to hydrogen, which is nonpolar covalent. Carbon to carbon, nonpolar covalent. What does B give me? The exact same thing that I need to answer my question. It's giving me the weakest force all the way through. I know that to be my answer. Okay? Getting the answer as B, you could have just guessed and said, oh, I got the answer right, and moved on. Okay? By going through and evaluating why the other answers are wrong can set you up. Okay? Get you to fix that. How do I now change the question to make one of the other answers correct? There's a really stupidly easy thing to do. Change it to now the lowest vapor pressure. What is the lowest vapor pressure then going to mean? It's going to mean less gas, which means high boiling point, which means strong forces, which then means a weak bond, which would be classified as ideally ionic as our weakest bond on our chart. Are any of our compounds ionic bonds? No. So this question now becomes significantly more difficult because I don't have an outright answer. I'm not looking at my ionic bonds, I'll be looking at my polar covalent. Okay. My polar covalent bonds will result in 2 different types of forces. Dipole-dipole or hydrogen bonding. Which force do I want to identify to answer the new question of now the lowest vapor pressure? I want the strongest force, which means I need to be looking for the compound that gives me hydrogen bonding. I now can backtrack through all my answer choices. I have to refine my answer because before I just said strong versus weak. And in that refining, I would find out my answer would now become A being the only one with hydrogen bonding. Okay? So what we just spent 15 minutes doing is what you should be doing for every single question in the practice exam. The practice exam is 68 questions long. Will that take time? Yes. I would hazard a guess that that will take at least a week, which is why you should have the practice exam answers done tomorrow so that you can be spending a week doing this processing. If you do this processing, you have already developed at least one other question that mimics that same type of question. Okay. Feel free to compare the actual exams you took and the practice exams. You will notice that processing is exactly what I went through and did. Okay. Subtle changes to the question. I don't have to rewrite a whole new question. Okay. All people are inherently lazy, including test makers. Okay. So to beat a test maker, you have to be less lazy than them. Okay? Questions on that one? I'm going to say no, because you guys are looking distractedly bored. So let's move on. Solubility. Okay, we've briefly looked at solubility. What is solubility? I'll half accept you pointing at the screen. Okay. It's the ability of anything to dissolve in a liquid. What is miscibility? Okay. Miscibility is a narrower definition of solubility. Solubility is the umbrella term. Miscibility is a subset within that. Okay. You could look at it as pie charts where miscibility, or the Venn diagram, where miscibility is a small section within solubility. Okay. What if it was not dissolving in a liquid? something did not dissolve in a liquid? What would I call that? Insoluble. What if it was a liquid that did not dissolve in a liquid? Immiscible. Okay? So IN or IM meaning the negative, the opposite of this. Okay? Can we use our forces to predict these solubilities? Yes. Okay? Which is kind of fun and fascinating. The rule of thumb that comes out of this is like forces dissolve like forces. Okay? That's how I phrase it. Okay? You've probably heard that before, but you've heard it as like dissolves like. Well, like what dissolves like what? Okay? It's coming back to identifying the intermolecular force in your compound. So if we take a look at our first example, H2O and ethanol. You all remember how to name ethanol, right? It's good. You shouldn't, because you didn't learn it. Would we expect those two to be miscible or soluble? What do we have to identify? What's our rule of thumb? What's alike? Nope. The forces. What are the forces in water? What is the strongest force available to water? Hydrogen bonding. How do we know that? We look at all of the bonds. We have a bond between oxygen and hydrogen. That is a polar covalent bond, which gets us a dipole-dipole force. A dipole-dipole force with hydrogen-bound oxygen, nitrogen, or fluorine generates hydrogen bonding forces. So our strongest force for water is hydrogen bonding. How about for ethanol? I have carbon bound to hydrogen. What force is that? Carbon bound to hydrogen? That is a nonpolar covalent bond, which generates our van der Waal or London dispersion force. Is that similar to hydrogen bonding? Okay. Said another way, is this, what color is that? Puce? Is puce like a green yellow? Green yellow. You've never heard puce?
No, hues.
Wow. Okay, so everybody's saying it's different colors, so let's just leave that out. It's yellow-green. Is yellow-green similar to black? No. Those aren't even remotely in the same ballpark. Okay, no one's going to look at your shirt and say, that is a yellow-green shirt. And let's avoid the color of the dress argument. Okay? Nobody's going to look at that and say that's a yellow-green shirt. So you were right. Puce, for the record, is some kind of like pinky, purpley brown. There is a picture on the internet that shows pink and the yellow-green. And the pink says puce, the green says not puce. So there's even an internet meme to explain how wrong I am. Phenomenal. Okay. Regardless, the thing I'm not wrong about is yellow-green is not the same as black. Okay. Those are not similar. If they're not similar forces, would we expect them to mix? No. But remember, in our analysis, we need to stick with the strongest force. Is London dispersion the strongest force in ethanol? No. I also have a dipole-dipole force due to the polar covalent bond between oxygen and hydrogen. Oh, but I have hydrogen-bound oxygen, which means I have hydrogen bonding. Is not puce the same as not puce? Yes. So are they similar? Yeah. What does that mean? That's not my finger, it's my elbow. Those would mix. Those are soluble or miscible. What happens if we switch over to the other one? How about water and propane? Water's force, we said, was Hydrogen bonding. What force did we expect from carbon to hydrogen? How about carbon to hydrogen? Or, okay, so our strongest force for that one is London dispersion. Is hydrogen bonding similar to London dispersion? No. Which means not soluble, or insoluble, or immiscible. Okay? So being able to look at a structure, recognize the bonds, translate that to the forces, then allows us to translate out to a physical observable, a property like solubility or melting point or boiling point or vapor pressure. Okay. This is a bizarrely super important topic that somehow gets relegated to the end of the semester because it doesn't really fit anywhere else. And if you go through and look at the practice exam, you will find of all of the concepts discussed in the practice exam, this type of force comparison shows up a lot, because it is incredibly important, even though it makes up such a small part of our overall curriculum. Okay? So you can fully expect lots of questions on this. I would highly recommend you study it. Yes?
For solubility and miscibility, is there a version of that with gases?
Officially, we did that actually with gases. Okay? Propane is a gas. So the next part is addressing this gas versus liquid thing. You notice miscibility just says liquid, dissolve, liquid. Solubility says anything to dissolve in a liquid. So gas in a liquid absolutely fits under solubility. Do we have a subcategory for miscibility? Turns out gases are considered liquids. Yeah, I know. Don't shoot the messenger. Okay. What? Gases have very similar properties in how they interpret and interact with things in comparison to liquids. That miscibility officially applies to gases and liquids as well. Okay. When we look at water and ethanol and propane, all three of those involve covalent bonds, not ionic. Okay. So typically when we're looking at our solubility versus miscibility, we're referencing, covalent bonds or covalent bonded compounds. What happens if we bring in ionic compounds? What is the solubility of sodium chloride in water? What is the solubility of sodium chloride in water? It's a lot of fancy terms. Should we change the terms around a little bit? Does salt dissolve in water?
Yes.
Okay, there we go. It dissolves in water. We should be able to apply these same rules that we just identified with our forces back to this. The strongest force in sodium chloride? Ionic. The strongest force in water? Hydrogen bonding. Is our yellow-green similar to red? No. So why does it dissolve? We end up getting a secondary layer of things that help contribute to that. When we're looking at that similarity, we run into, again, this kind of scale. Hydrogen bonding is probably up at that yellow end. The ionic compound of sodium chloride is probably more like the orange. In comparison, yellow and orange, right next to each other, they are fairly similar and they dissolve. So when we look at a compound, we go, oh, that's just a yellow compound. Okay? It is the peach terror alert today. Okay? Those color scales are difficult to align and process and work through. Okay? But they do kind of distract us from the overall idea. Okay? Most ionic compounds dissolve in water. Okay? For the reason that when I dissolve salt in water, I have a nice figure on it. Yes, I do. When I dissolve salt in water, water generates some very nice kind of dipoles for me. I get a partial positive from the hydrogen, a partial positive from this hydrogen, and if I drew in, say, my chloride with a negative charge, I can look at that single interaction there. Come on, different color. Between the partial positive of our hydrogen and the formal negative of our chlorine. If I compare that to the interaction here versus here, which would I expect to be stronger? Would I expect the purple interaction to be stronger or the red-green, our Christmas? Ionic is weaker than ionic dipole? Not Christmas. Our ionic will absolutely be a stronger interaction. But that then suggests that salt should never dissolve in water. Why is salt dissolving in water? We are not comparing one ionic interaction to one not ionic interaction. We're comparing one ionic interaction to a lot of not ionic interactions. The sum total of that contribution of all of those individual water molecules interacting with the ions of our ionic compound is what allows them to dissolve. Okay? Which is very, very tricky to process. This is a solubility sphere, okay, or a solvent sphere. It's a complex topic that gets lots and lots of study. All you really need to recognize is that most ionic compounds are soluble in water, which is a good thing. Anybody know what your DNA is? It's ionic. If it was ionic and it didn't dissolve in water, we're going to have a bit of a problem getting access to our genetic information. Okay? Yes?
So would this be like a stepping stone into concentration for certain compounds?
This does step up eventually into concentration, because to get it to dissolve, we have to have enough waters around each particle. What happens if we stop running out of waters to get around it? It won't dissolve anymore, and you can't dissolve any more salt or sugar or anything else for that matter. Okay? Are there exceptions to the solubility with ionic compounds? That was not a good exception down there.
Assuming yes, but
How about silver chloride? Would I expect silver chloride to dissolve in water? Well, the bond for silver chloride is an ionic bond, right?
correct.
So shouldn't that then dissolve in water? It's an exception. So our ionic compounds have all sorts of exceptions. You might go, well, God, Mike, why are we now talking about more exceptions? These aren't more exceptions. These are exceptions you already learned when we talked about solubility rules and what type of reaction? Beyond a chemical reaction, yes. Double replacements. Okay? So, you were close. So you are responsible for recognizing those and working within them. Okay? Like dissolves white, like to predict which of the following liquids to be miscible with water. What does miscible mean? Dissolves it. That should really say like what? On an exam, I would expect to see that, even if it's in a multiple choice answer. Okay. The reason being is you've now added an interpretation to that. You don't have to think as hard. Instead of interpreting the English of the question, which is there to confuse you, you've converted it into a process that allows you to interpret a little bit easier. That can simplify your process. So like forces dissolve like forces. So we're looking at those compounds. Well, like forces, 1. Like forces, 2. But our answers only show one thing. What's the second? Water. Since I'm looking at like forces, I shouldn't be looking at water anymore. I should be looking at hydrogen bonding. My best answer will be hydrogen bonding, or like hydrogen bonding dissolves like hydrogen bonding. Which of my answers gives me hydrogen bonding? Okay. D. And I can jump to the answer relatively quickly by doing short little interpretative steps that allows me to get my thoughts on paper, and I can get to the answer relatively quickly. We've been talking about this now for 45 minutes. Never mind the extra 75 minutes we talked about it on Tuesday. You might have said, well, didn't I get D right away? Okay. What happens if you spend 65 minutes on some other topic? How quickly are you going to be able to jump to that answer? Not very. But by writing down the information that you know, you can shorten that jumping distance within your cognitive load, and you can get to your answer quicker, okay? And more accurately. Write stuff down. Okay? Questions? Okay. Now we're going to do a big, big shift. Okay? H2S, H2SO4, H2SO4AQ. What is the name of H2S? And since you're all kind of sighing, I'm just going to make you write them all out. I want to see them on. We just have to name the first one and the second one. Sulfide. We change the ending of the second one because it's more electronegative. So we end up with hydrogen sulfide. But because this is a covalent compound, we must specify the amount of each of those elements. So is hydrogen sulfide correct?
No.
It must become dihydrogen. And then we can get nitpicky if you wanted to and add in the monosulfide. I tend to just ignore it because I think it's dumb. I'm sure nomenclature thinks the same thing about me. Second one. So we have hydrogen and we have sulfate. That is the complex ion of sulfate, one that you are required to have memorized. Okay. If I write hydrogen sulfate out, I'm going to end up with, is that the same thing that we were asked for?
No.
No. It needs to become dihydrogen sulfate. Last one. Well, it's the same thing as the second one, right? So we just write dihydrogen sulfate?
No.
Why not?
Aqueous. Acid.
Aqueous and the hydrogen in front, which means it gets named as an acid. Which acid? Binary or ternary? Ternary, which means we take the sulfate ending, we change the ate ultimately to an ick, but sulfur is just freaking weird, and it becomes sulfuric acid. Why am I mentioning this? A couple reasons. Number one, guess what's on the final? Nomenclature. Yes, that blank. Okay. You are responsible for nomenclature. Not only does it show up as an explicit, what is the name of this compound, but you will also see blank reacts with blank, what is the product? If you don't know how to convert the name into a formula, you can't go through and predict the reaction. Okay? So you need to know your nomenclature. Why else did I mention it? Kind of a hint at the top of the page. Starting with acids and bases. Guess what H2SO4 aqueous is? An acid. We're looking at our acids. Why does sulfuric acid get a different name than all of the others? Really actually has nothing to do with it being aqueous. Somebody got this little vat of sulfuric acid together, stuck their hand in it, and it burned their hand off. And went, holy crap, I don't want anybody to touch that. I'm going to name that. That was the pain that I felt. It was, or if we sat in it. Maybe that's a better way of looking at it for our acids. Okay? They had a giant beaker of this liquid, and they sat in it, and they go, that's an acid. That was no. Okay. I'm not repeating it because it was bad enough. Okay, we have our acids. Okay, those are dangerous species. We recognized fairly early on in history that we don't want to stick our hands in acids or get near them because they hurt us. Okay, because of that extra level of chemistry associated with them, they got their own special name. That's why we name it according to that acid rule, because we're trying to call attention to avoid that. Yes?
Don't bases burn you too, though?
Bases have the exact same issue with them, and I've still not found the historical reason on why we don't label bases quite as dangerously as we do acids.
Because it has to be more, it has to be more potent.
Nope,
than,
it does not. It absolutely does not. Your bases are just as dangerous as your acids, and it has nothing to do with potency. They will both do the same thing. It may be, yeah, I don't know. So, some quick observations that came out. Some observationalists noticed that some of these compounds happen to be sour tasting, and they were also sticky feeling. So yeah, good question. How do you find out sulfuric acid is sour tasting? Maybe you diluted it a whole lot and then made somebody you didn't like drink it, and they're like, oh, this is sour, and then they died. And you're like, I know, it was sour. And now we need to name that and make sure nobody else drinks it again. Okay. Are there acidic compounds that don't kill us?
Yes.
Lemons, okay, oranges, all have citric acid. Okay. That acid characteristic does not necessarily mean it's going to kill you or melt your face, okay, but it does have that same level of chemistry associated with it. Okay. And we can recognize that on our milder acids. So acids tend to be sour tasting. Bases tend to be bitter tasting. Okay. This may not apply to anybody in here because I think it was considered kind of a form of torture. Anybody growing up when you were caught swearing, your parents shoved a bar of soap in your mouth?
But I thought it was soap.
What does soap taste like?
So, I get those flavors.
I'm not going to technically recommend you go home to taste soap, but it tastes pretty bitter.
So wait,
Yeah.
is the whole thing with soap like both?
Soap is purely a base. Okay. And what you are tasting with that soap is a bitter flavor. Okay. It's again associated with it. The sticky feeling is characteristic of acids, primarily because what is it doing? It's dissolving your skin, exposing more polar substances. Those polar substances on your different fingers can now stick to each other. That's pretty awesome. Yeah.
When you spray people down.
So if coffee's bitter and a base is bitter, can you like throw coffee on something to neutralize it if you want?
Depends on the strength, but yes. Yeah. The slippery feeling. Bases are slippery feeling. Why are they slippery feeling? The polar part of your soap is interacting with the polar part of your skin. The non-polar part of soap is now aimed outwards. The non-polar parts then rub against each other and slide across. Okay? With our stronger bases, if we didn't look at soap, what's happening is the soap is reacting with the cell membranes and taking your cell membranes and turning the individual fats and lipids in your skin into soap.
Oh, that's
Yeah, really pleasant.
There was.
Yeah. Okay. So bases are slippery and bitter tasting. Acids tend to be sour tasting and sticky feeling. When we combine an acid and a base, what do we end up doing?
Water and
We form water and a salt in what is known as a, don't tell me chemical reaction, double replacement, more accurately, a neutralization. Okay? So, our first definitions of acids and bases went all the way back to, I think he's Greek, Arrhenius was the one at least credited for it, so we get a definition according to him. He noted that when species were dissolved in water, he noted that there was an increase in the concentration of hydrogen ion. Okay? I don't know the specifics of how, but that's what he was able to detect. So when we took hydrochloric acid and or hydrogen chloride and I added it to water, I saw a large concentration of hydrogen ion appear. Okay? That gas that kind of was just floating around in normal, added to water, now burned me. Okay? Or corroded me, because acids tend to be labeled as corrosive. Okay? He also noticed that when some species are added to water, that they increase the concentration of hydroxide. Okay? So in his observation, and then he said, okay, what happens when we mix those two species? Well, we mix them and we've done a neutralization, a double replacement. Our NaOH with our HCl. Okay? So he defined these two or acids and bases according to these definitions. Our acid was defined as increasing the concentration of hydrogen ion, and our base was defined as increasing the concentration of hydroxide. These definitions, okay, are technically quite useful within general chemistry. Why would they be useful in general chemistry? What is the solvent used in general chemistry? Water. So when you're doing any reaction in general chemistry, you are adding something to water. In the process of adding it to water, if the hydrogen ion concentration goes up, you have an acid. Okay? If you add it to water and the hydroxide ion concentration go up, it's now a base. Okay? So it's great for general chemistry. But what about the real world? Quite frankly, sucks. Okay? It is such a narrow definition on acids and bases that it only applies to hydrogen ions and hydroxide ions. There is a multitude of reactions that it does not cover, okay? Which is why we then refined that later. Okay? So we had a pair of scientists, Bronsted and Lowry, then get responsibility for the next one, noted that yes, we are seeing these changes in hydrogen ion and hydroxide ion, but some species don't produce hydroxide. Okay? Don't react as in that top one. When we look at that top one, we added HCl to NaOH and we produced water. Okay? When we talked about our neutralizations, we said water and a salt. Well, there it is, water and a salt. What happened in the second reaction? I got ammonia. No water. So was that a neutralization reaction? What happened to the acid? Do we see the acid as a product anymore? No. So what did I do to the acid? I neutralized it, but we just said it's not neutralization, right?
Isn't it called standardizing?
Okay. So we've run into an issue. We've created a new chemical situation where the definitions of acids and bases don't apply very well. Okay. So Bronson and Lowry said, okay, let's change our definition. Okay. Acids, again, characteristically the most obvious or ever-present chemical out there, they kept the acid definition as a proton donor. Did I mention proton yet? No. I did not. So give me a second. Hydrogen donor, okay, a hydrogen ion donor. They changed the definition of a base. Okay. What did the base, or which species is the base in the first equation? Which species was the acid? HCl. In the second equation, which species was the acid? HCl. Which species was the base? Okay. In the second equation, no hydroxide appears. Okay. So I need to come up with a new definition that allows me to identify NaNH2 as a base using a definition that still applies to sodium hydroxide. So what happened to the sodium hydroxide? What happened to the NH2? We wrote that out instead, whoops, as HOH. The hydroxide in the first equation accepted a hydrogen ion. What did the NH2 do? We went from NH2 to NH3. What happened to it? It accepted a hydrogen ion. So what they did was simplify the definition down. Instead of being two separate definitions about two separate species, they refer to the acid as a hydrogen ion donor and the base as the hydrogen ion acceptor. Okay? The base is the thing that accepted the hydrogen in the process of running that reaction. The acid is the one that gave it up. Okay? those definitions are still really, really narrow, but they're broader enough that they tend to be a fairly commonly used definition that applies well for both general chemistry and organic chemistry. Okay. You notice that I already slipped in referencing these. Okay. I said a proton. Okay. What is a proton?
Semi-atomic.
It is a subatomic particle, yes?
I was gonna say.
It is a positively charged subatomic particle. That is what a proton is. Okay. What is a hydrogen ion? So our symbol for hydrogen ion would be what?
H+.
So what is a hydrogen ion?
What she said.
A hydrogen ion is a charged hydrogen atom. Okay. How is it different from a hydrogen atom?
Hydrogen atoms would be charged.
Why is a hydrogen atom not charged?
Because it's not an ion.
Nice circular work. Admire that.
Well, if it's not noted in the little upper right-hand corner, don't we just assume it's at like its natural?
Okay. If we looked at a hydrogen atom, okay, we could just write it like that. Let's add some more information to this. What other information could we add? What information would we specify here?
It's atomic mass.
The atomic mass, which should be 1 for hydrogen. The atomic mass for all hydrogen elements is 1.01. What do we specify in the lower left-hand corner?
Atomic mass of symbolic.
Close. It's the atomic mass for a single hydrogen atom, a single isotope. What dictates the mass for a single isotope?
Protons, neutrons.
The protons and neutrons. So if we look at hydrogen and we say 1, how many protons and neutrons do we have?
One proton, no neutrons.
1 proton and
One.
no neutrons, because neutrons contribute. So I only have 1 proton when I look at the hydrogen ion. How is that different from my hydrogen atom? Doesn't my hydrogen atom have 1 proton?
The electrons that we're looking
If it still had a neutron, I would have to change the mass.
at the electrons.
What's that?
We're looking at the electrons.
A hydrogen atom has what else? 1 electron. To become a hydrogen ion, how do I become positively charged?
Get rid of the electron.
I get rid of the electron. So a hydrogen ion is what?
A proton.
Freak of nature.
A proton. So when we refer to our acids and bases, sometimes you'll hear people say hydrogen ion donor or hydrogen ion acceptor. You'll notice that I didn't. I refer to it as a proton donor and a proton acceptor. Why can I call it a proton? A proton and a hydrogen ion are one and the same. Why do I call it a proton and not a hydrogen ion?
Good, easy.
It's easier. Proton is a shorter word. It's easier for me to reference. So we tend to refer to our acids and bases in our second definition as proton donors and proton acceptors. Kind of make sense? Okay. So now we can come up with this idea of conjugate acids and bases. So if we take a look at that top reaction, okay, what would you predict each of those species to act as? What would you predict either one of those to act as? So we can call it A and B. Okay, we're looking at the acid and base chapter. One of them is probably an acid, one of them is probably a base. Which one's which?
Well, isn't the
A and B was just arbitrarily picked.
We're gonna do X and Y instead.
What do you mean they're in order already?
Because
H3O plus is likely an acid, and why?
Because acids you can only have an acid if it has an hydrogen.
Acids donate hydrogens. H3O plus has hydrogen, so it could act as an acid. Does SO3 minus 2 have a hydrogen?
It's a base.
Does it have a hydrogen?
Negative.
No, so can it act as an acid?
No.
No, so what does it act as?
Base.
A base. For SO3 minus 2 to act as a base, what must it do? It must accept hydrogens from an acid. So what would its structure look like if it reacted?
Negatively charged, so more electrons in the protons. Let's be wrong.
I'm not sure what question you're answering, but you're not answering the question I asked. Okay. If sulfite acts as a base, what happens to it? It must accept a hydrogen. So what would it look like? What would the formula be? Accepted a hydrogen, right? It's now HSO3. Okay. When we're doing our acid-base reactions at this level, we only want to do one at a time. So that simplifies things. Okay. HSO3, I've accepted one hydrogen. What would its charge be? Just minus 1. Why only minus 1?
Because it only accepted one proton.
It only accepted one proton. The proton was a positive charge. A positive charge with a minus 2 charge gets me a minus 1. The other product? H2O. What happened to H2O or H3O plus? Because it acted as an acid, it lost a hydrogen, and it becomes H2O. Okay? What I want you guys to do, what are we, Thursday? By Tuesday, is predict products for the bottom equation, and I expect those products shown up on the boards at the beginning of the chemistry class, and then we will go through and label our conjugate partners. Okay? The more responsive the class is, the faster we'll get through the material, and the faster you guys can actually ask questions relevant to the exam. The slower, the more I'll take time on answering, going through the slides, and we may not have any time for review. Just so you